The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Rowney.
Welcome back to the podcast. Hey, Kevin, how are you?
Hey, man. How's it going?
Good. I'm excited for our interview today. We're going to be talking with Rob Schoelkopf from the Yale Quantum Institute. Rob is quite the pivotal figure in quantum computing.
Kind of a big deal.
Yeah, absolutely. I mean, my own career in quantum computing started at IBM Quantum in 2017. I started working with them and then formally joined in 2018. Jay Gambetto, of course, the leader of the R&D efforts there, came from Yale. So that was where I first heard Rob's name. And then it suddenly started to dawn on me that Chad Rigetti, the founder of Rigetti Computing, also came from Yale. Jerry Chow, who is leading the hardware R&D efforts at IBM, also from Yale. Alexandre Blais from University of Sherbrooke, also from Yale. Even John Martinez, although he wasn't at Yale, but he had an affiliation with Michel Devoret, who was at Yale, and he was the leader of the effort at Google. So really, Rob and Yale's fingerprints are all over superconducting qubits right from the beginning. And that's because Yale's was the institute that came up with the transmon architecture, which really unlocked the practical implementation of superconducting qubits. So, quite the contribution already to this field.
Well, this is going to be great. I can't wait. Let's dive in, man.
All right.
Well, hello and welcome back to the New Quantum Era. We're really delighted today. We're excited to have Dr. Robert Schoelkopf as our next guest. He's the Sterling Professor of Applied Physics at Yale and also the director of the Yale Quantum Institute. Professor Schoelkopf is amongst the key foundational contributors to the dawn of what we call the transmon era of quantum computing. He is also a leading scholar on the subject of circuit quantum electrodynamics. He and his team today are highly active contributors to the advancement of new discoveries in quantum computing. Welcome, Dr. Schoelkopf.
Hi, it's nice to be here.
Yeah, we really appreciate your time. Thank you so much. It's such an interesting story arc, right? The dawn of the transmon and what it's then led to in terms of new advances in quantum computing. Such a rich and complex landscape. Can you help our audience sort of understand the new advancements that might be happening with respect to this architecture and where it might go next?
Sure. Maybe we can also start with some of the arc of the history. Quantum is pretty new, but I count as an old timer, I think, in the space.
You go back some, yeah.
I started my lab at Yale in 1998 when all we had was one trapped ion qubit. And, the basic question there was, could we make something that was like an integrated circuit that would follow the rules of the quantum world with superposition, entanglement, and all of that? And, we were able to answer those questions very much in the affirmative. And, kind of to my surprise, by the 2008, 2009 or so, things had gotten to the point where we could run in the university lab, algorithms on a few of these qubits. And in particular, this transmon that you mentioned had gotten to the point in both performance and kind of repeatability, stability, that it was clear you could start scaling things up. And this is when we sort of saw the dawn of the industrial push into quantum
Yeah.
computing with superconducting qubits. We had a slightly different take on things. That probably the very first thing you could scale might not be the best thing or the most efficient thing to scale. And in particular, my research then shifted over to trying to find efficient ways to solve the problem of quantum errors and quantum error correction. And so it's, been a progression, a lot of new ideas around things. And now we have this new approach called the dual rail qubit, which I've been sort of saying is like as the transmon is to making superconducting qubits themselves robust and easy to make and scalable. The dual rail is kind of that solution for quantum error correction in my mind. It suddenly relaxes a lot of the requirements and gives you an entry point where you can start really building machines that are beyond the NISQ devices that we have today.
Super interesting.
That's great.
Yeah.
And Rob, like before you started working in superconductor or quantum computing per se, you were involved in single electron transistor design and research, right? Was that sort of what brought you over to quantum computing, or how are those related?
During my postdoc at Yale in 94 through 97 or so, I was kind of transitioning. I had been working in superconducting devices, but in a group that did radio astronomy, millimeter wave astronomy. And I had also worked for a couple of years at NASA's Goddard Space Flight Center on cryogenic detectors for astrophysics. So I was very, much in the how sensitive a measurement can we make? How do we make a gadget that can detect something no one has ever detected?
Right.
And during my postdoc, we kind of found ways to apply some of these microwave techniques to the domain of nanostructures and tiny quantum electronic devices. And so it was very good timing and very fortuitous, because that was also right around when Shor found his algorithm and showed that error correction was at least mathematically possible.
Right.
And everyone started, saying, well, how does one make a qubit? And at that time, I was like, well, I think we know ways to make qubits. It's going to be really hard to measure them, but I think I have the tools and I know how to do it. So let's give it a try.
Right. I just find that interesting as well, because Yasunobu Nakamura had mentioned that single electron transistors and the work in that domain had been quite sort of influential in his works, and he was sort of first Cooper box kind of circuit, so part of the prehistory of the superconducting qubit. So it's an interesting connection. And then Kevin mentioned circuit QED. That's sort of the coupling of the understanding of the quantum dynamics of photons and microwave photons to the actual superconducting circuit, right? That's addresses, as you said, the challenges of readout per se.
Yeah, we use the term circuit QED to cover all the set of ideas that are basically parallels to cavity quantum electrodynamics. That's the source of the name, or cavity QED, which is when you have single atoms coupling to single photons in the optical domain. And what we've sort of been able to develop, and this turned into the kind of quantum computers that IBM, Google, and others have out there now, is a way to make the equivalent of an artificial atom out of superconducting circuits and Josephson junctions, and the equivalent of optical photons, but in the microwave domain just at a few gigahertz. And that combination then led to ways to not only have quantum bits, but have ways to, as you mentioned, control and measure them and couple them together.
Right.
And so then you have sort of all the necessary ingredients at the physics level to think about making a quantum processor.
To actually do compute.
Yeah.
Interesting.
So you said you're sort of focusing on error correction. Obviously, when Shor's algorithm was unveiled or discovered, the first reaction was great, but you'll never be able to run that because qubits are so noisy. You're going to need error correction. Shor then follows up the factoring algorithm with the first error correction algorithm. Real 1-2 punch. I've yet to find anything comparable in the field to what he did, but that was really an adaptation of classical error correction to a quantum regime. And then you've got Kateev sort of bringing a quantum native approach with toric codes and then the successor sort of surface code. You mentioned that the qubits that you're building out, QCI, are sort of the transmon for error correction. Is it more of a classical approach implemented in a quantum regime, or is it a quantum approach, a native quantum approach?
It's a quantum approach. These dual rail qubits that we're now building are like a small logical qubit, or they're an element which is more complicated than a standard qubit because it has the capability of detecting the errors natively. That's kind of built into the hardware. And they're also, devices where we're seeing really exciting levels of performance. So, we have coherence times that are in the milliseconds, so longer than the standard transmons. We have state preparation and measurement that's a couple of orders of magnitude better. And coming soon, we'll be publishing some things on gate performance that's really quite remarkable. So I think what we wanted to do was kind of in our stealth mode originally at QCI, figure out how to get something really robust that wouldn't require you making millions and millions of qubits to have a fault tolerant machine.
Right.
You don't want to scale and get tiny factors of improvement. You want to have something where when you implement the error correction on top of these dual rail qubits,
right,
you're getting gains that are an order of magnitude with each layer of error correction or something like that.
Amazing.
Yeah.
Amazing.
So and this is really looking pretty good. I mean, the way we try to explain this is that our strategy is correct first, then scale,
right,
rather than scaling up and trying to do a brute force approach to conquering the errors at some later stage.
And if I'm not mistaken, I mean, some of these are very recent breakthroughs. I mean, press is just emerging
they
today
are.
on some of these.
Yeah. I mean, we started with implementing the microwave photons as really the information carriers rather than the transmons. And there were these various ideas such as cat qubits and other things, which then led to the dual rail, which is really an idea that only comes in the last 2 or 3 years,
right,
but is already being implemented at scale at QCI because we've done all the background work. We had the engineering team in place that knows how to build this novel kind of architecture. So it was really, kind of things coming together quite a bit after a long period of development in the last few years. And the innovation is really moving very quickly now. We've already sort of gone through 4 different ways of doing the entangling gates, each one improving on the last, just in the last year or so. So,
well, it's so interesting. Again, it feels like a cutting edge breakthrough just emerging in the press today. But I mean, I'm wondering for our audience, perhaps this term, a dual rail qubit might be new to some of them. Is there some,
it will,
I don't know, easy and convenient way to summarize that architecture and how it distinguishes from what went before?
Yes. In transmons, it's basically the information is stored in the presence or absence of a single excitation. The dual rail is just slightly more complicated. You have 2 oscillators, 2 places you can place a microwave excitation, and the excitation is either in the left or in the right, but the qubit should always definitely have an excitation present. And when you see that there's no excitation present, you've lost the qubit's information, but at least you know. And it turns out that when you're doing that, there's sort of 2 implications of this. One is in the near term, you can run algorithms and say, here's 1,000,000 shots, but these are the 1,000 that actually work.
Interesting. Yeah.
Okay.
Yeah.
And so you can get higher fidelity in sort of short depth circuits. And that's really going beyond the noisy intermediate scale machines we have today, where you run 1,000,000 shots and you're trying to pull the signal out of the noise. And it's a tiny fraction, maybe, if you're doing a complicated algorithm.
Well, and in fact, it's done statistically in post-processing, right? You get a giant sample set and you try to discern which ones after the fact might have been a success or unsuccessful.
That's right. So the error detection is kind of a hack, or it's a little bit of a cheat. But if it's a cheat that gives you better performance, then you have a leg up for doing these other kinds of error mitigation or other types of things. And it incorporates. I mean, part of the thing we've always been building at QCI is focused on solving the problem of error correction, which means you need to be able, even when you're making a surface code or something like that, you need to be tracking the errors, following them in real time, and responding. So your control system and your whole architecture has to know about that and be able to do low latency measurements and the like. And then the second implication of this dual rail and the error detection is that you can embed those qubits into various kinds of error correcting codes. And now you have an advantage. It's sort of simpler to correct these so-called erasure errors where the photon disappears than it is the usual kinds of errors. And in our dual rails, the remaining errors are an order of magnitude or so below the sort of dominant detectable error.
So interesting. So does this maybe open up the possibility of brand new quantum error detection algorithms, or is it rather that this new architecture is so suitable for many of the extant algorithms already available?
Potentially a little bit of both. I think it's a very interesting time in quantum error correction. It started conceptually a couple of decades ago, but there wasn't really contact between theory and experiment until just recently. And the idea now that you can evolve your code or design your code to match the hardware, and you can optimize the hardware to get the best out of certain codes. This kind of co-design is common in conventional computing, but we weren't able to do that in error correction because we hadn't reached this stage yet. Yes. So I think we're really at a tipping point for Quantum Circuits Inc. and also for error correction and for the field now, where we'll see things that are again beyond this NISQ era, and we're starting to see things where you really can implement error correction. And the goal here by correcting first and then scaling is that we don't have to scale as much. You can be much more efficient. If you're gaining faster, you won't need this massive overhead of thousands of qubits per bit of compute in the final algorithm.
Right. You mentioned erasure qubits or erasure errors where the photon disappears. Are there advantages for detecting and correcting bit flip or phase flip errors in the dual rail qubit as well?
Yes. So the structure of the dual rail means that the phase errors are limited by the intrinsic phase fluctuations of these microwave cavities that we use to store the photon. And that we can't measure. It's at least milliseconds or longer. We've just placed a bound on it. And then we also understand that at least when it's idling, the dual rail basically doesn't have bit flips. So we've placed a bound on the bit flip time that's sort of 1/10 of a second or something.
Wow.
And so now you feed that into an error correcting code, you give it that knowledge, right? And it makes the very tricky problem of locating, finding, and undoing the errors that much easier, because in the ordinary approaches, like, it's possible, but it's incredibly complex.
Yeah.
And that's where this overhead sort of expands on you. And people talk about, well, I don't know, is fault tolerant computing a decade away because we need to get to millions of these elements and we only have 1,000 today? We think it's going to be faster than that.
What's your guess as to sort of the range for the ratio of physical to logical qubits for your architecture?
So, if you can really gain this order of magnitude or more as you increase the distance of the code, you can get to these kind of error rates of 10 to the minus 10 with only sort of 10 layers of error correction rather than 30 or something, which people often talk about. So it's, you're talking about an overhead of several hundred qubits per logical, not thousands or 10,000s. So it can be orders of magnitude efficiencies is what we're going after.
Right.
And, I think there's also a very interesting thing, which is, what does it take to get the quantum advantage? We've been talking about regular machines that have no error correction and are just noisy, and then some far off domain where the computer is basically like a digital computer and errors are completely suppressed.
Right.
Well, we're never going to get to that final stage. You're always going to use your quantum computer on the bleeding edge of failure, because if you can reduce the overhead of the encoding and have just a few more qubits, you're gaining exponentially in the compute power you get. And so you're always going to have something where you're trying to use error detection to suppress the leading errors, or correction to suppress the leading errors, detecting the remaining ones, mitigating the ones you can't deal with, and sort of pulling all those tricks out of the hat to get the answer that you're looking for.
And the output will always be a sample set from which you analyze, not an answer.
I think so. I mean,
Yeah.
I think we're going to sort of be in an area where now with the machines that we're bringing out at Quantum Circuits, we can explore this kind of domain of partial error correction and how you combine error detection and error mitigation, and making error aware machines and learning how to program them and how to design algorithms with them. So we're excited to have our users get their hands on this and see what the community can do in terms of creatively coming up with solutions that leverage these new features. So,
well, that's exciting. So, I mean, how soon will that become apparent? I mean, we're going to see QCI up on the Amazon cloud soon?
Yeah. So we also have our own portal, and we have an alpha user program. So we've had our first users already running on some of our small machines, and we've just had a press release today announcing the launch of a device we call Acumen Seeker, which is an 8 dual rail qubit that has these unique functions of error detection and real-time control flow. And so, we're, now coming to the industry with something that's, qualitatively different, we think. And we understand that we can scale this up, but even with, modest sized machines, you're learning new things because of the new features.
Of course. Well, and you mentioned programming this device. How different is gate and circuit sort of creation and engineering from a quantum developer point of view?
Right. So this architecture and the dual rail qubits have the usual universal gate set of single and 2 qubit entangling gates. And so you can run any algorithm people have drafted in Qiskit or the like. What you can also do, though, is you can insert features like detect, along all the qubits at this stage in the algorithm and find out which ones have errors. And then you can, respond to that. You can say, okay, the top part of this algorithm actually succeeded. Let me only use the information from that part of the computer. Let me maybe reset this qubit and see if I get some partial answer that's still usable. And, you have the ability sort of now to do this feed forward and so on, which, by the way, is required for fault tolerant computing when you do things like teleporting in magic states and the like. I guess we're getting pretty technical here, but
that's okay.
The idea is that, the quantum machine actually requires a sophisticated classical controller that can respond. And, there's also an interesting possibility that people are starting to talk about, which is combining in real time some, classical compute and quantum. You can use the results of one of these measurements. Maybe it's not detecting an error, but it's a measurement of some part of the algorithm, and then you want to respond in real time. So you can make kind of adaptive algorithms as well, even if we're not worrying about errors. And so
is this variational quantum eigensolvers or an evolution of that idea?
So I guess the VQE or variational eigensolvers would be one instance, but they're really something where you run, maybe 1,000 shots at least of the QPU. You look at some averaged output, and then you have a slow loop that's doing some feedback to try and optimize and find the actual solution to the chemistry problem. What we're talking about is something where within a single shot, you're actually able to make a measurement and respond. And so you can have kind of iterative algorithms and the like, right? So
the control system is perhaps inside the QPU, not outside.
Our control system sits at room temperature outside the refrigerator, but it has sub-microsecond latency in which it can measure and then respond. And so, that's still 1,000 times shorter than the coherence time. So there's a lot you could imagine doing in that time.
And
Interesting.
you just mentioned, the sort of the physical implementation. You've been addressing sort of the scalability of the error correction approach. There's the whole other several dimensions of scalability for superconducting qubits, which is, how much can you fit, how many leads can you fit down into a dill fridge, those types of. So yeah, I mean, what do you see as sort of the physical challenges to scalability that you need to address?
Yeah, so I think indeed the complexity of the wiring in the control system is, a problem we know how to solve, I would say, but requires investment and some hard engineering. Um, it's, another reason for us taking this approach of efficiency is that, we want to squeeze more compute out of, when you have 1,000 wires in each cryostat. The other thing that's exciting that people don't talk about that much in circuit QED or superconducting devices is that you can actually convert quantum information into flying photons that travel on a transmission line or a coaxial cable. And, if you imagine some large machine that can be modular, having different blocks that you separately build and test, you can put those all in one cryogenic environment and have these microwave interconnects between them. So, that's a way to kind of help with the scaling. You don't have to have everything crammed onto one chip, for instance.
That's really interesting. It's almost like a bus of, in computer technical architecture jargon, a bus of communication between separate
Exactly.
computing subdevices. Yeah.
In 2007 or so, we published a paper showing sort of a quantum bus and being able to connect two transmons and entangle them over sort of centimeter distances where they didn't actually talk to each other, but they were still on a single chip. There have been since then experiments showing, physically converting to a cable and then going to a really separate module and being able to generate entanglement in that
Wow.
way.
Wow. Really fascinating.
Yeah.
Well, and so for these new approaches, I wonder, are there frontiers yet to cross on the engineering to make these chips at higher density and higher scale of manufacture? I mean, many of these issues in the fabrication labs are by no means an easy challenge to overcome.
Yeah, that's right. I mean, we take a modular approach sort of from the beginning. So our devices are not a monolithic thing on a single chip. They're actually multi-chip modules where there are a few elements like a transmon ancilla, its readout electronics and the like on a single chip, and then the thing that couples you to the nearby devices is another chip. And what we're seeing is that's a really nice approach. If you're trying to make a chip with many, many devices and you have to get your yield to the point where all 1,000 devices on a chip yield, that can be hard. Whereas in this modular approach, if we assemble a system, cool it down and test it, and there are a few devices that are out of spec, it's possible to sort of pull those individual chips and replace them. And so, my point of view is the size of the block you should be building as you build a quantum computer is always the largest quantum unit that you can very reliably build and test, right? And as we get better and better with the fabrication and our control, that size of that block will grow, but you always want to be connecting. You always want something bigger. So you always want to be connecting up several of these blocks. And so that's also been a sort of signature of our research and of the approach at quantum circuits.
That modularity that you've designed into the system allows that kind of growth. Yeah.
That's right.
Really interesting.
Yeah.
Wow, such a cool new frontier. I mean, there's so many bits of hype in this space that people, I think, perhaps make a bigger deal of these advances than perhaps they are. But this particular innovation, it does feel like it opens up a whole new angle, right, on what could be a realistic route towards large scale in the nearer term future. Am I putting too much spin on this? What do you think?
No, we think this is really a breakthrough that will allow us to scale up more rapidly. I mean, that's going to take a little bit of time and some more resources, but I think this dual rail architecture feels to me like something that's really worth scaling at this point. We tend to be very conservative with our claims, but I'm pretty excited about the recent results we've been seeing, which are coming at a very fast pace as well.
From my perspective, everything you're claiming has been backed up with actual experimental results and numbers you can see in a paper on archive.
Yeah.
So,
I think it's important to show what you've got, and it's going to be a longish road for getting quantum computing there, and we want to avoid overhyping and under delivering on promises and people's expectations. And so, as a field, we should be cautious, I think. And one of the reasons I decided to get into the commercialization space and found quantum circuits was that I thought we had things to bring that other people weren't really considering, and that I sort of had a responsibility to be like contributing to this in a deliberate way, and try to be a good example in our academic research, and that's, I think, shown up in where our graduates are. They're leading many of the efforts out there in the field, and they've been successful scientists on their own. And so, we sort of felt like, that approach was the one we should take with quantum circuits, and be careful and deliberate and not overhype things, and wait till we have, real proof before going forward.
Yeah, so real path breaking work here, but a sober-minded view of the future.
That's the scientist in me.
Refreshing.
Exactly.
Thank you. Yeah.
Yeah. Well, so much of the challenges in quantum computing are bridging that gap between the scientific foundational work that needs to be done and as you said, the engineering or technological or even business challenges required to sort of get to implementation at scale and practical advantage.
Right.
So if the
thing I get asked very often is like, is quantum computing now science or engineering? And my answer is yes.
Yeah. Right.
Right. And I think it's only scientists who have no idea or experience with technology transfer and development that would think you do like science, and then all of a sudden you throw it over a wall and it becomes a product.
So they work it out.
And so, that's one reason I've maintained my role at the university is I think there are still innovations that, are best explored in the high risk, high reward, it's okay if it fails. And at the same time, if you're on the industry side, you can't try to scale something that you don't have an existence proof of, right? You need to know what it looks like, and you need to be nimble to incorporate new innovations as they come. And that's tricky, and that's going to be hard for the entire space. But it's something that one can do if you're careful.
Right. And in part, I think also the confusion and sometimes frustration around the difficulty in predicting timelines in quantum computing comes from people sort of making category errors about, you can look at whatever the portable computing from the first luggable to the iPhone and go, well, that was a series of engineering advances primarily. And somewhat predictable in kind of timescales from one step to the other. And with quantum computing, you've got certain tasks require those high risk, high reward breakthroughs to actually figure out how to solve the problem. And those are very hard to put error bars around. How much time will that take? Not sure.
Right. And everybody knows about Moore's law. But you don't think about all the work that went into materials science and device physics along with that allowed us to have the amazing miniaturizations and advances.
Yes.
So I think we're going to need the equivalent of that in quantum, a robust research environment and people pushing on the technology side.
You brought up Moore's law. I've heard people refer to Schoelkopf's law, being that the time of coherence doubles every what was it, 2 years? I think, is something
it
like
was
that.
10x every 3 years, and it did that from starting with Nakamura's first experiment in '98 up until about 2010 or 2015, and things have gotten hard. It's kind of plateaued,
Is that
and
so?
so
Wow.
there's been maybe another factor of 10 in the last decade or so, and people have been really concentrating on um, the scaling, but we've also been working hard on the coherence. And in our devices, we currently use these three-dimensional microwave cavities, which can have longer lifetimes and much less noise than the standard transmon circuits. So you're always going to be able to build a better resonator than you can build a qubit, in my opinion.
Right,
So.
right. So looking out a year from now, where would you like QCI to be? Where you hope you are in terms of the development of the technology?
Right. Well, I mean, we're very excited to have our machines getting into the hands of users and seeing what they can do with them. I think in parallel with exploring that commercial space, we've got some ambitious plans about demonstrations we can do with error correcting codes in this next year or two. And so I think the race is on to sort of show an error correcting code that really gives a dramatic improvement, right? So we did the first experiments with cat codes in 2016, where we corrected the natural errors. It was just idling, just a memory operation. And we could just barely get some gain. We were overcoming the overhead and like 10% extra. And in the recent experiments with 100 transmons, they now get a factor of 2 gain. But a factor of 2 for 100 transmons, that's pretty hard work. And so, I think, if one can show error correction that really has, large gain, and you suppress the errors by a factor of 10 or more, that's really a, tipping point, or, I mean, it's really the proof that fault tolerant computers will be built.
Yeah, it's a
Right.
whole new
And
game at that point. Yeah.
yeah, and I think that's, as you said, when Shor first introduced error correction, people wondered, would it ever really be practical? I think we know the math works. We know that in principle you can do it, and it kind of works. Can it really be done in practice and efficiently enough that you would benefit by putting error correction into your machines? And
Yeah.
that's the thing that we think we have a clear path to proving.
God, this has been
Incredibly
so
exciting.
fascinating. We
Yeah.
really
Yeah.
appreciate your time. Thank you, Dr. Schoelkopf.
Yeah. Thanks a lot. Been great to chat with you guys. A lot of fun.
Wow, that was just amazing. Another one of these great interviews. That was kind of cool, don't you think? Hearing about these brand new
Absolutely.
architectures for QC, these dual rail systems, man, it's quite a breakthrough. Seems like. I guess just press breaking just today on the topic. We'll probably get a link up on the
That's
posting
right.
of this episode. But yeah, it does sketch a whole new future, right? Of what might be a brand new framework for big scale, way better gain, way better error correction.
Right.
Still a long way to go. I really appreciate also he's got this inspirational view about where things could go, but also a very sober-minded attitude about, just setting expectations. There's still many innovations left to make progress against before we're at a commercial system.
That's right. Yeah, we do seem to select our guests based on the clear-eyed view of where the technology is today, and Rob was no exception. I mean, I think there are really significant. What I found really exciting is the idea of entering into a new phase of real co-design between theory of error correction and experimental implementation of at least something that is more aware of the error correction approaches that are going to be, that makes intuitive sense that that's a way to drive higher efficiency and lower ratios of physical qubits to logical qubits. And that, of course, lowers the bar in terms of the challenges for making these devices at scales that will be commercially, advantageous.
Absolutely. I also really appreciate his attitude about how this is, a mix of both, physics theory and, engineering practical problems that must be in collaboration in a very constant and very intense way to make progress against this target. It's not just the scientists on one side of the room and the implementers on the exactly
collaboration.
Yeah, that's pretty cool.
I mean, that's what keeps me glued to this space. Absolutely, is that it feels like a rewind to the middle of the last century when we were still trying to define what classical computing might be, and it was a direct collaboration between physicists and engineers for the first time back then around information theory and computation. We get to do it all over again with the extra challenge of doing it at the quantum level, and that's just catnip for me. I mean. I can't stop thinking about it myself. So
it's
hence
amazing.
The podcast.
We live in miraculous times. Yeah,
absolutely. Cool. All right, Kevin. Until next time.
Thanks, man. Good times. See you around.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Rowney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.